will be asked in the chat, and now cameras and microphones must be turned out. I give the floor to Professor Alexander.
Okay, so welcome back after lunch. And this afternoon, the material, it's a bit more advanced, it's a bit more up to date, but I'm not going to present it in a very technical way. I will omit technical details, which, if the ideas interest you, can be found in papers, but try and give you a sense of these new ideas. So let me share my screen. And go into full screen. So I think you are looking at chapter 2, Attainability of Kendall rank correlations. And I'll go back to the motivation, which is when we have limited or non-existent data, and we may want to incorporate expert knowledge about correlations. And we have to make sure that it makes sense when we do this. And so there's one example that I'll do towards the end with some cryptocurrency data. Let me show you the data now. I actually have data on 4 cryptocurrencies, but we're going to pretend that these are 4 risk factors and that I only know about the first 3, and I have limited information about the 4th one. And like I said, there's a paper which I wrote with 2 people last year, which explains the ideas in great detail. So here's the 4 time series. Imagine we didn't have the bottom one. So we don't have the blue one. We have more limited information, but we do have Bitcoin, Ethereum, and Litecoin. And over time, we can estimate correlations between these 3 Kendall correlations, but we'd like to say something about dependencies with a 4th risk factor. So I'll come back to that later on. And let me say what I mean by the attainability question. So we have a random vector. I've been calling it X this morning, and it consists of D risks, X1, XD. And the Kendall rank correlation matrix is the matrix of all the rank correlations. So it would be D by D. It would have 1s on the diagonal. And the ij element of this matrix would be the Kendall correlation between xi and xj. And so I'm going to call this matrix p tau, or like I said this morning, you could also call it rho tau, because this can also be seen as a Greek rho. And so the question is, well, what properties characterize this matrix? What kind of matrices can we get? And let me tell you 3 things that must be true. This matrix must be symmetric, because the rank correlation between I and j must be the same as the rank correlation between variable j and variable I. So you can change the order. So it must be symmetric. On the diagonal, it must equal 1, because the correlation of any variable with itself is 1. And off the diagonal, the entries must be between -1 and 1. Now, a third thing that needs to be true is that it needs to be positive semi-definite. So it can't have any negative eigenvalues. The eigenvalues must be positive. This is a known property of correlation matrices. So in fact, these 3 properties, symmetry, the requirement 2, and 3, positive semi-definiteness, these are necessary and sufficient properties for ordinary or Pearson correlation matrices. Every ordinary correlation matrix will satisfy these 3 properties. And moreover, for any such matrix, we can find a distribution such that that is the Pearson correlation matrix. So for any matrix that has these properties, it is attainable. I could create a distribution that would have that for the Pearson matrix. But I'm interested in the Kendall matrix. And what's interesting here is, although these properties are necessary, so they must hold, they are not sufficient for Kendall matrices. In fact, we need stronger conditions. So this, these three properties, they will definitely hold for a Kendall matrix, but it's not enough. If I have a matrix where these properties hold, I can't be certain that there will be a distribution for which the matrix will be the Kendall correlation matrix. And so that's what I mean by attainable. I need to know that there exists a distribution that can give me these correlations. If there's no such distribution, then this is a logical impossibility. Now, in order to explain what the real condition is, I need to say a little bit more, I need to say a little bit about extremal copulas and extremal correlation matrices. So this slide is perhaps a little bit theoretical, but in dimension D, we can think of an index set J, which is a subset of D. So it could be 1 and 2, could be 1 and 3, it could be 1, 2, and 4. It's any subset of D. And suppose we were to create a random vector with the property that the jth component was U, if J is in this index set, and it's 1 minus U if J is not in this index set, where U is just a single uniform random variable. Now, if you're wondering what's going on here, we've used this construction this morning, and I just want to show you in the R where I did this. So if I come out of the full screen and we go back to the R, so you maybe remember these pictures that are appearing in the viewer. So this is a copula where both components are the same, U1 equals U2, and this is a copula where U2 equals 1 minus U1. And so these are examples of the construction that I'm talking about. So either the variable J is U or it's 1 minus U, and it all depends on the index set. Excuse me. Okay. Now, such a vector will have uniform marginal distributions because they're all either U or 1 minus U. And if U is uniform, 1 minus U is uniform. But the probability mass will be on a diagonal of the d-dimensional unit cube, or the unit hypercube. We can actually calculate the expression for the copula corresponding to J. So the copula corresponding to J, it takes this form. We take the minimum of the elements in the index set, or the minimum of Uj for J in the index set. We add the minimum of Uj for J in the complement of the index set. We take away 1. We have to take the positive part. And we've already seen one special case of this construction in dimension D, which is the comonotonicity copula. So if this index set were equal to the whole set D, so if it were equal to the whole set 1, 2, 3, 4 up to D, then this would be the comonotonicity copula. So the comonotonicity copula is an extremal copula, but in general, there are many of these extremal copulas in D dimensions. So there's more than one. Now, why is this called an extremal copula? Well, if you look at the construction, so the elements of the vector are either U or 1 minus U, then you see the following, that the Kendall rank correlation matrix of the copula C with index set J, then the elements are either 1 or minus 1. So the ij element would be 1 if both indices were in the set J, or if both of them were in the complement of J. Because let's suppose that both I and J are in the index set J, then the corresponding variables are both U, and the Kendall correlation of U with itself is just 1. On the other hand, if both of these, if I and J are both in the complement, then both variables are 1 minus U, and the correlation of 1 minus U with itself is 1. In fact, this is not only true of the Kendall correlation matrix. P tau would also be the Spearman matrix, I beg your pardon, the Spearman matrix and the Pearson matrix of C. So in fact, this copula has the nice property that the ordinary correlation matrix, the Kendall matrix, and the Spearman matrix are in fact identical. But we're interested in the Kendall matrix in general. So it's extremal because all of the correlations are either 100% or minus 100%. Pairs of variables are either perfectly positive dependent or perfectly negative dependent. So every pair is either comonotonic or counter-monotonic. So that's why they're very extreme kinds of copulas. They're sort of the most extreme copulas that you can get in this family. And in dimension D, there are precisely 2 to the D minus 1 such copulas. When the dimension is 2, there are 2, which are the ones that I just showed you in the R script. You saw 2 copulas. Those are the 2 extremal copulas when the dimension is 2. Each associated with a diagonal of the unit square. In 2 dimensions, the unit cube is just the square. And so the ones associated with the 2 diagonals were the extremal copulas. But when we have D dimensions, there are 2 to the D minus 1. We can order them in some way. And I won't go into that, but there are various ways of ordering them. But I'm just going to show you a picture which makes this a bit clearer. So what about if we go to dimension 3? So in dimension 3, 2 to the power 3 minus 1 is equal to 4. So there are 4 such copulas. And in my ordering of them, the first copula is concentrated on the red diagonal, and the second copula is concentrated on the blue diagonal, and so on. And so these copulas are distributed on a diagonal, but they are copulas. They are multivariate distributions with uniform marginal distributions. So that's the key idea. And now I can come to the characterization of attainable Kendall correlation matrices. I have what I need. So I'm just going to tell you this. The proof is quite long and a bit difficult. I mean, not very difficult, but it would take a while to explain. You'd have to invite me for longer and you'd have to want to hear all the details. So let PK be the extremal correlation matrix of the kth extremal copula. So when D is 3, there are 4 of them. And so we would have 4 matrices PK, P1, P2, P3, P4. And this is a theorem. So the D by D correlation matrix P, it's a Kendall's tau rank correlation matrix if and only if it can be represented as a convex combination of the extremal correlation matrices in dimension D. So if you can write P as a weighted sum of PK, where the weights, they must be positive. Okay, so they must be, or at least non-negative. They could be 0, but they must be non-negative, and they must sum up to 1. So that is the condition. As long as we can take a correlation matrix and we can write it in this form, then it can be a Kendall rank correlation matrix. Remember, not every correlation matrix, that is not every symmetric positive definite matrix with elements in -1, 1, not every such matrix can be a Kendall correlation matrix. But if it can be written in this form, then it is. Any matrix which can be written in this form, we can find a distribution that will have that Kendall rank correlation matrix. And the set, so this describes a set of matrices, and that set is called the cut polytope. So it's a convex set, it's a weighted combination. So another way of saying this, if you've studied convex analysis, perhaps in mathematics, is that the set is the convex hull of these extremal correlation matrices. But that's just fancy language for saying that you can write it as a weighted sum. And the set, it actually has a name because it turns up in other applications, and it's called the cut polytope. And in 3 dimensions, it looks like that. So let's suppose in 3 dimensions there would be 3 values of tau. So when we look at this set, we can just look at the off-diagonal elements of the matrix. So really it's a set of matrices, but if we just consider the off-diagonal elements, which are, in the case of 3 dimensions, there are 3 of them. We have the correlation of 1 and 3, sorry, the correlation of 1 and 2, the correlation of 1 and 3, and the correlation of 2 and 3. And they've got to live inside that gray shape, which is called the cut polytope. And so any point outside of that shape is not attainable. It would not be attainable. And I'm going to, in R, I'll give you examples which illustrate that. So that's the cut polytope, that particular shape. It's not so easy to display it in higher dimensions, which is why I show you this nice picture in 3 dimensions. So not all correlation matrices are attainable Kendall matrices. And here's an example of one that isn't. So firstly, observe that I'm dividing every element by 12. That means that there is a 1 on the diagonal. So the diagonal is 1s. And off the diagonal, the element is -5/12. Well, if I were to plot the point, -5/12, -5/12, -5/12, if I were to plot that point, it wouldn't be inside this pyramid here. It would be outside it. It's not actually attainable. But this is a perfectly valid Pearson matrix. This is a symmetric matrix. It is positive definite. It has non-negative eigenvalues. It does satisfy the value constraints. And so it is a Pearson correlation matrix. I could make a distribution that has this linear correlation matrix. I could make a multivariate normal that had this linear correlation matrix. I could make a multivariate student that had this linear correlation matrix. But it's not a valid Kendall matrix. And the Kendall matrices are the ones we need in these Monte Carlo studies in order to put arbitrary distributions on risk factors. That's the whole point. If I want to put any distribution on a risk factor, I work with the Kendall matrices because then I can do it. Now, if we tried to find the weights, so suppose we tried to find weights which made this matrix equal to a convex combination of the extremal correlation matrices. Well, we could find weights. The problem is one of them is negative. So in fact, these 4 weights, what you find is there's a linear equation system and you can determine weights, but as soon as one of them is negative, as this one is, you know it's not attainable. And so that's how you test it. You look for the weights, and if they're positive, it's fine. But if one of them is negative, it's not attainable. Now, there is some good news when you have data. When you have data, and when you estimate the rank correlations from data, then if there are no ties, so ties means when you would have equal values for some data points. Now, when there is an underlying continuous distribution, the probability of tied values, so the probability that you see 2 x1 values that are the same or 2 x2 values that are the same, that probability is 0 when you have a continuous distribution. In practice, you can have rounding effects. If you round returns to 2 decimal places, then there's a chance that you could have 2 returns which have the same value. So in practice, you can get ties. But if there are no ties, then the standard estimator always gives a matrix which is attainable, meaning there is a distribution that will have precisely that Kendall rank correlation matrix. So that's good news. In the nice case, where you have data from a continuous distribution and therefore with probability 1, no tied data. Right, so how do we test for attainability? So I'll go through the theory and then we'll have a look at this in practice again. So I decided to keep it simple and really just tell you roughly what's happening in order not to get too technical. But it is really about linear programming, linear equations. So the theory of testing for attainability, we have to look for solutions of a linear equation system. And I'm going to tell you about the vector on the right-hand side. So the vector on the right-hand side, we take the Kendall correlations. So we have tau 1, 2. In theory, we would have tau 1, 3, tau 1, 4. Depends how many variables we have. The last one would be tau d minus 1 d in d dimensions. So in 4 dimensions, the last one would be tau 3, 4. We add 1 and we divide by 2. We add 1 and we divide by 2. That's because what actually goes into this vector are not the Kendall's tau values, but the concordance probabilities. So I'm just going to jump back to one idea from this morning, if we can get there. Yeah, so tau is related to another measure called a concordance probability, which you see, which you can't highlight it actually. I'll just put my mouse over it. So tau is related to another measure called a concordance probability, or in other words, the concordance probability is tau plus 1 divided by 2. Okay, tau is twice the concordance probability minus 1. The concordance probability is tau plus 1 divided by 2. And it's actually those numbers that go into this vector here, concordance probabilities. W is the weight vector we're trying to find. And remember, because there are 2 to the d minus 1 extremal correlation matrices, this weight vector is of length 2 to the d minus 1. The matrix A, I'm not going to go into that in detail, but let's just say it's a known matrix and all its elements are either zeros or ones. So it's a known matrix and it will have as many rows as there are correlations plus 1. We always have a 1 in the first element here because that 1 corresponds to the sum constraint. The first row of the A matrix is only 1s because the first row gives the sum constraint that the weights must add up to 1. The weights, so the W's must add up to 1. So the first row is 1s. And then there are another d times d minus 1 divided by 2 rows. And there are 2 to the d minus 1 columns. So if you do the maths, then if d is less than or equal to 3, this is a full linear system. And either there is a unique solution, let's put it this way. So there's either a unique positive solution or no solution. By no solution, I actually mean that the weights could be negative. So either there is a solution with positive weights and there will only be 1, or there's a solution with negative weights, which I actually call no solution because I want positive weights. So d is less or equal to 3 is quite easy, but if d is greater or equal to 4, there will either be multiple solutions or no solution. So there will be a set of possible solutions, so more than one weight vector. And when there are multiple solutions, they will also form a convex set. So a convex set, meaning that you can take linear combinations of them and they will still be in the set. Now, if certain values of Kendall's tau are missing, because we don't know them, then we just delete the rows. So we would just delete a row of this vector and we would delete a row of A if certain Kendall's tau values are missing. And so what I want to do now is to show you that a little bit more slowly in R because it will start to make more sense when you see what I'm doing. So let's go into R and let me make that now full screen. Okay, so the piece that I'm going through now is the second section here, attainable Kendall correlations. And so firstly, I want to show you a non-attainable matrix. I'll show you a different one. So here's a set of values for tau. There's a very nice function called P2P, P2P, which is not my function, it's in the copula package. But when I do that, it turns it into the matrix. There's the matrix. So you see I have ones on the diagonal, and the first correlation is 0.8, the second is minus 0.2, and the third is 0.3. So P2P takes these values and it turns them into the matrix. And so why is that not attainable? Well, in order to do that, I have to make a vector called kappa. Kappa consists of 4 numbers. The first is always 1. The second is the concordance probability corresponding to a Kendall tau of 0.8. The third is the concordance probability corresponding to a Kendall tau of minus 0.2, and so on. So these numbers are actually the concordance probabilities. They go into the algorithm. And the algorithm is coded in find extremal. So it looks for weights. And so if I were to run that, I would get some weights. And the problem here is that one of these weights is negative. So remember, in 3 dimensions, there are 4 diagonals of the unit cube. So they have, the way that they're named, basically it's, what the naming means is that this is the diagonal. The first one is the diagonal that connects 0, 0, 0 to 1, 1, 1. The second is the diagonal that connects 0, 0, 1 to 1, 1, 0, and so on. So these specify different diagonals. And one of the weights is negative. So I know immediately that this tau matrix, this one here, P to P tau, I can't have that. I simply can't have that as a Kendall matrix. If an expert comes to me and says, that's what I want, I would say to that expert, I'm sorry, you can't have that because that is nonsense. We just can't have that. It's logically inconsistent. So, and that's quite important in these methods, that it's a perfectly valid correlation matrix, because if I do this, if I take this matrix, which I've called P to P tau, then the eigenvalues, these are the eigenvalues, they're all positive. So it's fine as a correlation matrix, as a linear correlation matrix, but we can't have it for Kendall. Here's one that we can have for Kendall. So I'll make another one. So say we do that one. Now we've got 0.2, minus 0.1 and 0.5. To check that, we have to make the kappa vector as kappa. These will all be positive, these numbers, because they are the concordance probabilities. There always has to be a 1 in the first position for the sum constraint. And then we can have that. If we took 0.4 times the first extremal correlation matrix, 0.2 times the second, 0.05 times the third, and 0.35 times the fourth, that would give us what we want. So if I show you what I've written, in this case, if you look at the viewer, perhaps it's slightly easier to read. In this case, we should be able to calculate or construct a copula that has the matrix P tau as Kendall correlation matrix. And the first thing we might want to check is whether we could get it from an elliptical distribution, like Gauss or T. And there, what we have to do is we have to work out under a transformation if we get non-negative eigenvalues. So this goes back to the theory I had before. From a correlation matrix, you can compute the Kendall tau. From the correlation matrix of the copula, you can compute the Kendall's taus. And so if we take the Kendall's taus and we work backwards, that's what I'm going to do. I'm going to work backwards. So I have my Kendall matrix, P to P tau. That's my Kendall matrix. And working backwards, this is what I would have for the correlation matrix of the copula, for of a Gauss copula or a T copula. That's what it should be, that matrix there. And so what I have to do is I have to check the eigenvalues. So, and the eigenvalues are positive, so that's fine. So I could have that. So for example, let's do the Gauss copula. So what I do is I take a normal copula, that's a function in the copula package. So that's a normal copula. I take the I need to, the way it's done, I now have P, but in order to simulate it, there are too many parameters in there. So I use the opposite function. It's called P to P. Now I start with a big one. Excuse me. So I start with a big one, and I reduce it to the off-diagonal elements. So what this does is it gives you 0.3 minus 0.15, 0.7. So you get those. And that's what goes into the constructor function. The dimension is 3. Don't worry about the final argument. That's not so important. And so what I have here, cop1, cop1, I have a normal copula, dimension 3, and those are the parameters. And then I can simulate 2000 data from that one. And we could have a look at the data. I quite like the command pairs. So this shows you that I have 3 by 3 data. And you can see that there's particularly strong correlation, let's say, between variable 2 and variable 3. That comes from the 0.7. And there's actually negative correlation between 1 and 3. So between 1 and 3, there's negative, and there's positive correlation, but a bit weaker between 1 and 2. And this distribution that I've created, its Kendall correlation matrix is the one that I started with. So I started with P to P tau. That's what it should be. And if I compute what I have from the data, it is close. I mean, it's not going to be perfect because this is simulation. This is simulation, but you see for the data, the values that I get for the Kendall correlation are pretty close to the ones that they should be in theory, but because it's simulation, I don't get it exactly. But I know that the model I'm using, that matrix there is the correct Kendall matrix. So the theoretical correlation matrix is correct. So that's one possibility. But there's another way of sampling data with that. There's another, perhaps I'll show you this in the viewer. So I've simulated this one here, but there is another way of going about it. So a second possibility is to sample data from a mixture of extremal copulas. And as the name would suggest, this is a much more extreme kind of copula to use. So there is a function R extremal mixture. And if I take my weights, these are my weights, what it's going to do with probability 0.4, it's going to take a point from the first extremal copula. With probability 0.2, it's going to take a point from the second, the third, the fourth, then the third, then the fourth. So it's going to mix these 4 copulas. And if I do that, then I get this kind of data. It's always going to be cross-shaped because these are data which are on diagonals of the 3-dimensional cube. So the data are on diagonals of the 3-dimensional cube. So if we take a section, if we take a 2-dimensional section, we see a cross. But the thing is, the correlation here is again going to be pretty close. I mean, this is done by simulation. So what I wanted was, I wanted that one. and I'm pretty close. You could say that that one looks, let's do it again. Let's see what it looks like the second time. Yeah, it's a bit closer to minus 0.1, and let's try it again. The model is correct. Yeah, that one's even closer. So it depends. They could be, so they're going to, you're not going to get exactly the correlations when you sample, but the model has the correct correlations. I'm going to do a four-dimensional example, and the logic is similar, but things get a bit more complicated. So in this one, here's my matrix. So it's 4 by 4, and I've got a mixture of negative and positive correlations. And the thing about the four-dimensional case is that in this case, if we have a solution, we'll have more than one. It won't be unique. Well, there may be no solution, but if there is a solution, there would be more than one solution. And so the method is, to begin with, it's similar in that I construct a vector kappa. I call it the kappa, and that always has a 1 at the beginning, which is for the sum constraint. And then the remaining elements are the concordance probabilities coming from the Kendall correlations. So it's just 1 plus tau divided by 2. And it's a different function this time, because you'll see what happens when I run it. When I run this, in fact, I get 2 solutions. So I see that there are 2 vectors of weights. So they're called V1 and V2. And they put weights on diagonals of the four-dimensional cube. The four-dimensional cube has 8 diagonals, 2 to the power 3. It has 8 diagonals. And so one possible solution is 0.0425 weight on the first, and so on, 0.3575 on the third. So that's one solution, but another solution is given in the second row. So this is a situation where the Kendall matrix is attainable. So this Kendall matrix here, that is attainable. I know it's attainable because I have solutions. If I found no solutions, it's not attainable. So I know it's fine. It's absolutely fine. Now, the set of all solutions, for the weights is basically the convex set that contains the first point and the second. So it's actually a line between these points. And any point on the line would also be a solution. Now, the problem with this one is that if I look at the corresponding matrix of an elliptical copula, so I'm going to do the same thing as before. I'm going to try and find whether I could match this with an elliptical copula, but sadly, the fourth eigenvalue is negative. So what I have there is a perfectly legitimate Kendall correlation matrix, but it can't be associated with an elliptical distribution. It can be associated with a mixture of extremal copulas, but it can't be associated with an elliptical distribution. So I couldn't get that one from the Gauss copula or the T copula. I can approximate it. So there is a method that's quite commonly used, which involves adjusting the correlations so that the final eigenvalue becomes positive, just positive. So there is a kind of adjustment method that you can do to change the correlation matrix a bit so that it becomes positive semi-definite, but I'm not going to go into that. However, we can certainly generate an extremal mixture. So in this case, I'm going to use the weights. So I have the weights here. I have 2 of them. So I could take the first vector of weights. I could take the first vector of weights, or I could take the second vector of weights, doesn't matter, or I could take a convex combination. So I could do this. I could take 0.4 times the first plus 0.6 times the second. That would also be a permissible weight vector, that would also that would also specify a distribution which had the right Kendall matrix. But I'm just going to take the first one, and I've generated 5,000 data, and I'll compute the rank correlations, and you can see now that P to P tau, that's what I wanted. And you can see here that I'm pretty close. You can see that I'm really close to what I wanted. This time I took 5,000 data. The more data you take, the estimated correlation is actually going to converge to the value that you want as you take more data. So let me go back to the final. So yes, let me talk about the final example with the cryptocurrency. So yeah, we've done the 4-dimensional example, the cryptocurrency example. What we're going to find there, so I'll load the data and plot it. Those were the 4 time series. But let's forget about Ripple. Ripple's the final one. So suppose we don't have data on the final time series. Instead, we've got an expert who says he or she thinks it's 0.6. So the way we set this up, this is going to be my Kendall matrix. So I've just taken the first 3, Bitcoin, Ethereum, and Litecoin. And I'm going to add to that, first I'm going to take out the off-diagonal elements. And so what I've got here, I've got the 3 off-diagonal elements, and then the expert has told me that the correlation between Bitcoin and Ripple is 0.6. So I changed them into kappa as before. So again, it always has a 1 at the beginning. And the only thing here is I have to be a little bit careful that I name these things in the right way. So I attach the name empty to the first one, but the second one is the correlation between 1 and 2. So that's Bitcoin and Ethereum. The third one is between Bitcoin and Litecoin. The fourth one is between Ethereum and Litecoin. And the final one is what the expert says. So the expert says that comes from the correlation between Bitcoin and Ripple. So that's my kappa. And then if I look to see whether this is attainable, I have to look for weight vectors. And this time I find 10 possibilities. So I find 10 possible weight vectors that would do the trick. And as long as that's not empty, then that is attainable. So what the expert has told me is fine. That's fine, what the expert has given me, because I can find solutions. And in fact, from these vertices here, the next thing I'm going to do is I'm going to take these vertices and I'm going to translate them into Kendall's tau vectors. So I think I just do this and show you. That's probably the best. But what you can see here is that each of these vertices gives me the value that I want for 1, 2. It always gives me 0.28. Remember, I'm trying to get this matrix here. So the numbers have been rounded, but I want 0.28 there. I want 0.33 there. I want 0.36 there. And so you can see that I have what I want, 0.28, 0.33, 0.6, which is what the expert said, 0.36, which is this one. But the final 2 rows, they give me the possibilities for the missing one. So for Ethereum and Ripple, I could get those ones. And for Litecoin and Ripple, I could get those ones. All of those are possible. And if I just take out the, if you like, the missing ones, so what missing tau here is just I take out the final 2 like that. So I've got the final 2. And if I plot them, then in this plot here, These are the 10 points. So each one of these values is a possible Kendall's tau value for 2 and 4 and 3 and 4. And moreover, if I were to draw the convex hull, so imagine connecting these points with a line, and these points with a line, and these points with a line. So I do the convex hull, and I get a set that kind of encloses them all with straight lines. And anything in that set is possible, but nothing outside that set is possible. So for example, I can't get correlations that are, I don't know, let's take a value down here. So 0.75 and minus 0.5, that wouldn't be possible because it's outside the convex hull of these points that are distributed. So I'm going to go back to the slides to finish off this section. So back in the slides, I find them. Yeah, so obviously I've hidden the details. So I've hidden the details of why this works, but I've just tried to show you that there is a method here. So the one that I finished with, imagine we've not observed ripple prices. We only know Kendall's tau. Without the expert's information, there is a shape here within the three-dimensional cube. That's the inside this shape here, that's the possible values for the correlations with Ripple without any information about Ripple. So the possible values between Bitcoin and Ripple, Bitcoin and Ethereum, Bitcoin and Litecoin, they're in this shape here. If the expert comes along and fixes, I took a different value here. I took the value in the data. So this time, instead of 0.6, so the expert now says it's 0.196. As soon as you fix that, it's like taking a section through this. And then you see that there is a set here, and the permissible values for the two remaining correlations are in this set. And you can't have anything outside. So there's some tools here for helping experts make sure that they specify consistent systems of correlation. That's the idea. And once you have worked out whether a Kendall's tau matrix is attainable, so suppose P tau has been found to be an attainable Kendall correlation matrix, how do you get a copula that has that matrix? Well, in some cases, you can take the elliptical copula, like I said, but you have to test whether this matrix is positive semi-definite by looking at the eigenvalues. If it is, you're fine. You can have a Gauss copula with that Kendall matrix. You can have a T copula with that Kendall matrix. But it only works for some matrices, unless you can do it approximately, but exactly it only works for some matrices P tau. But for all matrices P tau, you can take a mixture of the extremal copulas. So in D dimensions, there are 2 to the D minus 1 extremal copulas in D dimensions. And so I can take a weighted sum of those ones, and that's what I did. So in the R, that's basically what I was doing. Where was I doing it? Well, maybe going back to, yeah, when I do this, R extremal mix, and I take the weights. R extremal mix, when I do that, that is what I'm doing here. I'm taking points from this mixture of the extremal copulas, and I can always do that if the matrix is attainable. So those are, but it's an interesting research question at the moment. What else could I do? Could I build other copulas? So that's an open question. I guess you maybe came on this course looking for solutions, but I can also give you open questions if you're a researcher. And one is, what else can you do? Which is quite interesting. So let me take a drink, and then in the remaining 25 minutes, I want to tell you about another interesting topic with copulas at the moment, and that's copulas for time series. So if it's okay, I'll continue. we should have time at the end for questions about what you've just heard. So I'm going to introduce it, and then I'm going to say something about ARMA copulas, divine copulas, and V transforms. So we're going to look for actually strictly stationary time series models for financial time series. So strictly stationary, that means that you have a model where at any point in time the distribution is the same, roughly speaking. So that's my aim. Strictly stationary time series models using copulas. And there is a growing literature on copulas and time series. There was a nice survey article in 2014 by Fan and Patton, but most of the literature is about how you model cross-sectional dependencies between series. And the literature on modeling serial dependence and volatility, for example, is more limited. And I've spent quite a lot of time in the last couple of years trying to add to the literature on copulas for serial dependence. So the idea is that we build copula processes. Let me actually make this full screen for the time being. So, okay, I've gone into full screen. So the idea is we make copula processes and we combine them with any marginal distribution we like. So we combine them with a marginal distribution fx so that we create a composite process xt for our data. And the idea is that xt and ut are connected by the probability integral transform. So if I transform xt by the distribution fx, I get ut at every point in time. So I'm going to be looking for two things. I'm going to be looking for copula processes, so stochastic processes whose distributions are copulas. And I'm going to be looking for marginal distributions. And again, we'll do this in R at the very end. And I'm going to concentrate on two core classes for UT, what I call ARMA copula processes, which I wrote a paper about, which was published in January, and divine copula processes. So those are the two we'll look at. And the divine processes, they're quite popular, or at least vine copulas are very popular. So there's quite a large literature on vine copulas. The constructions there are quite tricky to understand for the first time. So I decided not to go into great detail about vine copulas. They require a bit more time to understand how they work. But you'll get a sense of it, I think, in the models that I show you. Now, the final point I'll make is that in order to model stochastic volatility, we need something else which I call a V transform, and that allows us to actually build models that can rival Garch or exponential Garch or other kinds of Garch models, and are quite similar in their behavior to econometric models in the Garch class. So let me tell you what an ARMA copula is. So I've decided to define it somewhat formally. Suppose you take an ARMA process with Gaussian innovations. So when you study time series at university or elsewhere, most of the time you spend talking about ARMA processes. And whenever you see examples, the innovations are Gaussian. So the noise is Gaussian. ARMA processes have an autoregressive order P, and they have a moving average order Q. And I'm going to impose one further condition, which is that the process ZT has mean 0, and it has variance 1. And it's strictly stationary, so this is true for all T. Then if I transform every single term to uniform with the standard normal CDF, what I get is the ARMA PQ copula process. So I take every single term, ZT, and I transform it to uniform. And what I get is an ARMA PQ copula process, which I'm going to show you in Rs, and you see these things at work. So what are the properties? If I then take any vector, say I take the value at the time t1, the value at t2, the value at td, that distribution is a Gaussian copula, and the correlation matrix of the Gaussian copula will depend on the autocorrelation function of the time series. So you're probably familiar with the idea of an autocorrelation function of a time series process like ARMA. Well, the correlation matrix of the Gauss copula will depend on this. And if I took a consecutive block, so let's say I took the variables u1, u2 up to ud, they would have as distribution exactly a Gauss copula in d dimensions, where the ij parameter of the matrix rho or p is just the ACF in the value I minus j. So this is just the copula of a Gaussian ARMA process. And it will have p plus q parameters, where p and q are the values we put in here. There will be no further parameters. There will be exactly p plus q parameters, and it's standardized to have variance 1. So you can, I'll show you in R that you can estimate a model that combines the ARMA copula process with any continuous parametric marginal distribution. So we could take this ARMA copula process and we could take a student marginal distribution, we could take a hyperbolic, we could take some strange skewed distribution, and we could estimate a model using maximum likelihood in quite a straightforward way. If we do that, then the resulting distribution is actually meta-Gaussian. I used that term earlier. So that's the ARMA copula process. And the idea of the divine, so I'm just going to do the theory and then we'll look at it in practice. But the idea of the divine here is that we relax the Gaussian assumption in the copula. So here we have Gaussian copulas in the ARMA process. But what if we tried to get away from Gaussian copulas? So we can do that in the divine. So what I'm going to ask you to do first is to think about the ARMA copula process in the case where you have no moving average term. So the order Q is 0. So you could call that an ARMA P0, or if you like, an ARP copula process. Now, in the ARMA copula model, the ARP copula process, it can actually be described by P bivariate Gaussian copulas. So you have an interesting decomposition of the model, which allows you to describe it in terms of P bivariate Gaussian copulas. And they have the following interpretations. So C1 to CP. C1 is the copula of two adjacent values. So let's say the value at time t and the value at time t plus 1. So C1 is their copula. C2 is the copula of two values separated by one time step given the intermediate value. So there was a question this morning about copulas for conditional distributions. That's actually what's happening here. C2 is the copula of the conditional distribution of ut and ut plus 2 given ut plus 1, and so on. C3 is the copula of ut and ut plus 3 given ut plus 1 and ut plus 2. So the way you can think of this ARMA copula process is that CI can be thought of as the ith partial copula. That's because it relates to the concept of partial autocorrelation. So again, this will only make sense to those of you who have studied time series in a statistics class or in an econometrics class. You'll have heard about not only about the autocorrelation function, but the partial autocorrelation function. And so the parameter of the ith copula, the ith Gaussian copula, rho I, is actually exactly equal to the partial autocorrelation at lag I. So alpha I means the partial autocorrelation at lag I of the underlying AR process. So that's a representation you can have that this ARP copula process, so we've removed all the moving average, that you can describe it entirely with bivariate Gaussian copulas in this way, and it relates to the partial autocorrelation function. And so the idea of the divine is, well, what happens if we take every single bivariate copula and we strip it out and we put in a non-Gaussian copula, like T, or like Gumbel, or like Clayton. So that's the idea here. And that's what gives you the divine. And so really what we do is we take the C1 here, and instead of a Gaussian, we put in something else. We put in a non-Gaussian for C2, a non-Gaussian for C3, and we can do that P times for any P, any positive P. And we get something called a divine copula process. And so I've written a definition which works, but is completely non-transparent. So apologies for that. A strictly stationary copula process is a divine P process if for any T, its joint density has a certain form. But the key thing to see is that it's parameterized by P bivariate copula density. So here are the key points. There are P copulas involved in the construction. So we have a sum here, or a product here up to P. D is just the dimension of a marginal distribution, but P is the key parameter. They are all bivariate, and they can be any bivariate copulas, really. So they don't have to be Gaussian. If they were Gaussian, this would just be the ARP Gaussian copula process. So if all of these copulas were Gaussian, this would be exactly the same as the ARP process on this slide. But they can be different. And I won't even go into the construction of the R functions here. All I want to say is the following. Such processes do exist. They can be constructed, they can be simulated, they can be estimated. If C1 to CP are bivariate Gaussian copulas, the joint density of the divine copula process is identical to that of a ARP copula process, but they don't have to be Gaussian. So this is a way of getting non-Gaussian serial dependence. The joint density is actually much easier to evaluate than it first appears. Looking at that, it looks pretty horrible, but in fact, this joint density can be evaluated in a nice recursive way. There's a big, it all belongs to the Vine copula literature, the theory of how you do this. So in other words, maximum likelihood inference is possible, and I'll do some. We can use a mixture of Archimedean, Gauss, T copulas for these pair copulas. We can use what we want. And in combination with non-Gaussian marginal distributions, these models can improve the fit in many situations where you might use standard linear time series models. So they allow you to take, for example, in macroeconomics, so things that you might model with ARMA, and there are lots of these things in macroeconomics, like inflation time series or GDP time series, where you, or interest rate time series, where you might use ARMA. With Gaussian innovations, you can do non-Gaussian ARMA, and it's non-Gaussian in two ways, because you can have any marginal distribution, and because you can change the pair copulas in the autoregressive model. However, they cannot capture stochastic volatility using standard copulas. And so I'm going to come to that as a final point, but I think I need to make this a little bit more concrete now. So this is what I want to show you in R. This is what I'm going to show you in the time series section. I'm going to create an ARMA copula. So if you see here, I've just created an object called ARMA cop. And if you see in the bottom left, this is an object of class ARMA copula. And moreover, it's the copula process belonging to an ARMA model of order 1, 1, where the AR parameter is 0.97 and the moving average parameter is minus 0.87. You might think these are quite strange parameter choices. These give some quite persistent low-level dependence. We could take other things. We could actually put in anything here that gives you a stationary ARMA process. And when I plot it, here I have a time series. I've plotted 1,000 data. I've simulated 1,000 data from this time series, and I've plotted it and you'll see that every number is between 0 and 1. So suppose I break that into steps. So I'm going to break this into a couple of steps, and I'm going to first save the data like that, and then I'm going to do a histogram of the data. It should be fairly uniform because it's a copula process. So the marginal distribution is uniform. So, you know, if I simulate another one, let's do it again. Do the histogram, get a different histogram, but it should be uniform because it's a copula process. So I'll go back to the one I originally created, and that's the time series. Now, I can combine this with an arbitrary marginal distribution. And the way I do that is I specify a marginal model. So you see here, margin creates a marginal model. The documentation, I've written this myself, so it's a little bit rudimentary. But ST stands for student, and I have to tell it the parameters of the student distribution. So there's a degree of freedom, and there is a location and scale. So this just creates a marginal model, which is student with 3 parameters. And then this is put together with the copula model. So the model that I call ARMA student, it takes a ARMA 1.1 process, and it adds an ARMA 1.1 copula process, and it adds a student distribution using the command TSCM, which stands for time series copula model. And now if I generate that, you can see that what I have here, I've got a time series which has a student T distribution. Okay, so it has a student T distribution, and it has the serial dependence structure of an ARMA 1.1. You can check that if I do the ACF. You can see here that there's quite persistent but low-level serial correlation in this model. And so that's an example of an ARMA copula process. Now I'm going to do the divine. Now, these are autoregressive models. So I'm going to do a model of order 4. And I'm going to do it by putting together, just to make it really exotic, a Clayton copula, a T copula, a Frank copula, and a Gaussian copula. So I put them together. I pick some parameters. Don't worry about the rotation. I pick some parameters. And what I have here is an object of class divine copula. It's a divine 4. And instead of Gaussian copulas at every lag, I instead have a Clayton, actually a rotated Clayton, if you know what that, it means it's rotated through 180 degrees. I have a rotated Clayton. I have a student T with parameters correlation 0.4, degree of freedom 5. I have something called Frank's copula, which I haven't really told you about. And I've got Gaussian copula. And again, I can simulate it and plot it. So here's another time series. And once again, it has the property that these data are uniform. And so I could add a marginal distribution. I could go back and I could add a student marginal distribution to that. So that's a divine copula process. Now, the final thing, I'm going to, Joanne, it's 20 to 3. I'm going to take about another 5 minutes, and then I think there should be quite a lot of time for questions.
Yeah, don't worry.
Yeah. Good. So let's go back to the very final section of the theory. So this point that I'm making here, so far what I've shown you would be fine for many macroeconomic time series. Anything that uses an ARMA process, we can change the distribution, we can change the serial dependence copulas, what I call the partial copulas, but we can't capture stochastic volatility. That requires something else. And that's the idea of the V transform, in my opinion. So my final example is going to be Bitcoin again, just because cryptocurrency is flavor of the month. So I'm going to talk about something called the U and the V scales. So the U scale is the scale of the original data. So what you're looking at here, Bitcoin, you're looking at the time series. And on the original scale, I call that the U scale because I could look at a copula process for those data. I could try and find a marginal distribution for those data and a copula process for those data. But the V scale is what happens if I remove the signs. So you're probably aware that if you take a financial time series and you square it, or you take the absolute value, that you can find the serial dependence more easily in the squared process. If I did the ACF, suppose I did the ACF of those data, I would struggle to find much serial correlation. The autocorrelation function would look like the autocorrelation function of independent data, but these are not independent data. And if I did the autocorrelation function of the squared data or the absolute data, I would find serial correlation. So the V scale is the scale under a transformation that reveals volatility. So a transformation like the absolute or squared value is a volatility revealing transformation, because then you find in the autocorrelation function the evidence of serial correlation. Now, one other thing that one can do, suppose I do the following. So this is the idea of the V transform. I take the X data. So that's these data in the top here. I take the X data and I transform them to U using the empirical distribution function. So what I've done is I've taken the empirical distribution function of the X data and I've transformed them to U. At the same time, if I take the square data and I take the empirical distribution of the squared data and I transform them to V, and then I plot U against V, I get a V shape. And that's what I call a V transform. It's basically the relationship between the pit data for the raw process and the pit data for the square process. So that's what I mean by the U and V scale. The U is when you transform the raw data to uniform, and the V is when you transform the squared data to uniform. It doesn't have to be squared. You can take other transformations, but basically a transformation that removes the sign and concentrates on the size. So that's a V transform. So here's what I'm trying to say. If you have a volatile financial return series, you seldom see much evidence of serial correlation. But if you take the absolutes of the squares, you do. And if we attempt to transform the raw data and the squared data to uniform, then we find a V-shaped relationship. And this is not actually surprising. It's not surprising because you can show a very simple theoretical result. Suppose you have a random variable and it has a distribution which is symmetric around 0. And suppose you take the pit transform of X and you take the pit transform of X squared or X in absolute value. It actually doesn't matter. You get the same thing. Then you'll find that V is related to U by a perfectly V-shaped transformation. Okay, so this is twice U minus 1 in absolute value, and it is what I call a V transform. It's a uniformity preserving transformation. It must preserve uniformity because both U and V are uniform random variables. So this function that connects them must preserve uniformity, and that's what we call a V transform. And that's what I used in my conditional backtesting. If you remember, I had a question about that. It's the same transformation I used there. So to model the serial dependence in volatile data, what we do is we construct copula processes such that under a V transform, VT follows one of our models. So in other words, we don't model UT with ARMA or with Divine. We model VT with ARMA or Divine. Because we find the dependence on the V scale, we use our copulas on the V scale. But that implies a model on the U scale. So you get an implied model on the U scale, which is called either VT ARMA or VT Divine. And these are the things which can rival Gotch. And so my final practical demonstration. So I'm going to add V transforms to both the ARMA and the Divine copula process. So VTS copula, it makes a copula with a V transform. And so I make two, and I'll just show you what they look like. So the first one, the base copula is an ARMA copula. That's the process for V. And the V transform that I'm using is actually the very simple symmetric. There's a whole family of them. There's a whole family of these transforms, but it's the very simple symmetric one. And similarly, that would be the one with the divine copula. So here you see that the base copula is a divine copula with different pair copulas. And again, the V transform is linear. And then finally, I'm going to add a student T distribution to each one. So I'm going to add, we'll just look at model one. You can see everything that's gone into it. So it's model class TCM. The margin is student. The margin is student, and the copula has a V transform. It's based on an ARMA copula. But if I simulate them, then you see what I get. So I make both of these, simulate them, and plot them. So that one has an ARMA copula. This one has a divine copula. And if I show you the autocorrelation functions, what you see is that in the raw data, there is very little serial correlation. So if I take the raw data, there's almost no serial correlation. But if I take the absolutes, then you can see that there is serial correlation by construction. By construction, there is serial correlation. Let's take real data. So now I take Bitcoin. So that's, let's just blow up the screen again. So I take Bitcoin, and that's Bitcoin. If I show you the ACF of Bitcoin, you don't see very much. It's real data, but you don't see much serial correlation. But if I show you the absolute values and take the ECF, you see correlation. So it's just like the processes that I've created. You get the correlation when you look at the absolutes, or it really doesn't matter whether you take the absolutes or the square. So I could take the squares here. You get the same kind of thing with the squares. And so I'm going to show you a model here that works really well with the Bitcoin. So I take a model based on an ARMA copula. So I'm just about done. I take a model based on an ARMA copula. So it has an ARMA copula. It has a V transform, slightly off-center V transform. So rather than having a symmetric one, it's actually slightly off-center. The distribution I choose is the Laplace distribution, which is somewhat uncommon. You find some papers on modeling returns with Laplace distributions. A Laplace distribution is, if you like, two exponentials back to back. So instead of the Gaussian bell shape, or instead of the student shape, it's two exponentials back to back. But this actually works much better for Bitcoin than a student. And so what I'm going to do, I've made a full model, which consists again of it consists of a marginal distribution, which is Laplace. Don't worry about the parameters, because I've just put in any old parameters. I'm going to estimate them from data. And I've put in a copula process based on an ARMA copula. And I can fit it to data, which I've just done. So it's been fitted to the data. And these parameters have now been optimized. And the point is that this model, so this model here, can beat Gotch. So I'm going to fit a Gotch to the same thing. And what you see is that the copula model, you can get much lower AICs than with Gotch models, meaning AIC is something you calculate from the log likelihood. So we can actually get some superior fits using copula models for these data with stochastic volatility. There's not really enough time to do that full justice. The software has some plotting functions that show you the quality of the model. For example, there are model residuals, which should be normal in this case. They're not too bad. And then the marginal distribution of Laplace, that's for people who know quantile plots. The first one is for the residuals from the process. The second is for the marginal distribution, which is Laplace. Laplace is about the best one we could find here, much better than student or other distributions that people typically use for these data. It all depends on the data set. So to round off, what I really just wanted to say is that there's interesting research going on now about doing time series with copula models, and you can get a lot of flexibility and potentially get some. The great advantage is you know the distribution exactly, which you don't for a gauge model. You don't have a closed form for the actual distribution, but for these models, you know exactly what the marginal distribution is. They're really nice for simulation. So my summary, what should you take away? Well, as Jose said earlier, at least if someone says copula, you have an idea of what it is, a multivariate distribution function with uniform margins. In practical terms, I've come to the conclusion that they are most useful for scenario analysis or stress tests, because you can combine different distributions. When full data are available, they can certainly be estimated from data, but they become really interesting when you're doing scenario analysis with sparse or missing data, and even with expert opinions. And I tried to show that rank correlations can be really helpful when you are trying to work out how to pick a copula in practice. There have been recent advances in understanding the conditions for matrices of rank correlations to be attainable. I mentioned my own work, but there's another paper on Spearman correlation by Wang et al., which looks at similar things for Spearman correlation. And copula models for time series is an interesting area of contemporary research. It's a very nice paper by Thomas Nagler and co-authors last year, where they go from univariate time series for financial data to multivariate time series for financial data. Basically building on the kind of divine copula models that I have shown you. So yeah, hopefully you didn't find the afternoon, it would have been more difficult, I know, and somewhat technical, but hopefully it opens your eyes a little bit to some things that you can do with copulas that you perhaps didn't know about. And hopefully the morning at least was understandable and helpful for everyone. So I guess I could take some questions now.
Okay, thank you very much. We have one question. It's by Andrés Berenguer Alonso. Say, thanks, Alexander.